Good afternoon, ladies and gentlemen. Thank you so much for supporting the afternoon session. Okay, there's some people still coming, but we need to start. So we would like to welcome Dr. Ndanduleni Lethole. He will be discussing exploration of future magnetic and cathode materials through computer-based simulation. Dr. Lethole, the stage is yours.
Thank you very much. My name is Ndanduleni Lethole from the University of Forte. So in this presentation, I'll be showcasing the work that we are doing at the University of Forte that utilizes the CHPC resources. So I'll just quickly pass through the outline. So first of all, I will start by a brief background and introduction of who we are. We are based at the University of Forte, the Department of Physics, which is located somewhere 230 kilometers from here when you go inland, which is in Alice. So then that's the building of our department. You can see that it looks like a real university. So this is the current team that we have. We have myself as the principal investigator. Then we have one PhD student who is working on luminescent materials for dye-synthesized solar cells. And then we have a student who has recently completed his master's, who happened to be the first student in this group, who is doing cathode materials. And then we have another student who's doing manganese iridium alloys, and then we have another student who is doing manganese iron platinum alloys, and then the honor student as well, who is doing magnesium vanadium pentoxide cathode materials. Then we also have other two who are not utilizing the resources of the CHPC. These ones are doing nuclear physics. Just a background as to when the group started or when did we start our work. You can see from 2020, it was just myself, no student, nothing. That's when we started applying for the resources of the CHPC. And then in 2021, we had 2 honor students. One dropped out in 2022, and then we had 1 master student. Currently, we are sitting on 3 master students, 1 PhD, and also 1 honors, which are the ones that I've shown. Then we are hopeful, due to the applications that we have received this year, that we can go to 4 master students and then 2 for both honors and also PhD. So these are the approaches that we employ as a university. We have our own personal laptops, then we connect them through MS Login at the CHPC servers to run our calculations. Apart from the CHP servers, we do not have any other computing resources, so then CHPC is our only hope when it comes to running our simulations. So this is the methodology that we employ. Right now we have got Material Studio through the CHPC. Then we either create or download our structures from the materials project, and then we run them through CASTEP, and then we do DFT or DFT plus U for the transition metal oxides. And then after that, we perform optimization of all the materials. And then we can run various properties such as elastic constants, band structure, density of states, phonon dissipation curves, and also thermodynamic properties. Then we can also have, from optimization, we can get various properties such as structural properties, the enthalpies of formation, the magnetic moments, and also the elastic constant, and also macroscopic properties, which are your moduli. So that's basically what we employ to do our calculations. So in this presentation, I will only focus on 2 projects that have been done for some time. The other ones are still very much at their initial stage. So then the first project, it's on cathode materials, and then we mainly focus on calcium manganese oxides, and then we are also doing magnesium vanadium oxides as well. But we are focusing mainly on this kind of cathode materials, which they are called the post-lithium rechargeable batteries. The main reason why we are focusing on this kind of cathode materials is that we are looking at their ability to deposit uniformly on anodes and also intercalate also into the cathodes. And then also these materials, they also hold a promise of an increased electrochemical capacity, high energy density, and also material sustainability in terms of abundance. And then, of course, the growing concern regarding the availability and also the cost of lithium-ion batteries. But the main advantage that we are looking for in terms of this cathode material is the issue of their valency. As compared to lithium, which oxidizes as 1+, these ones they oxidize as 2+, as they appear in the periodic table. So then in that case, it gives them higher capacity in terms of energy density. So that's the main reason why we are looking at them. So, but however, the challenge with this kind of cathode materials, calcium and also magnesium, is the suitable host structure due to their nature of being big. So then it needs a structure that can allow reversible intercalation without the distortion of the host material itself. So then that is our main focus area, to find suitable host structures for calcium ion as well as magnesium ions. So this is a project that is done by a master student, the one who has just completed. So then he has investigated these 3 calcium manganese oxides materials. Then as you can see, they have got some sort of sufficient diffusion channels of calcium. So then this is what is of interest to us, to say that in this structure you can have good diffusion. And then also we are also interested in their bivalency, that in charging and discharging, instead of only one ion going in and out, then you are going to have 2 ions going in and out. And then the other thing that we are looking at in these materials is the large volumetric cell, which also gives good volumetric capacity, because their volumes, they are large naturally. So which means that you are going to deal with a very volumetrically large compound or cathode material. So then we have done some calculations on these 3 polymorphs. We have calculated their structural properties. We have calculated their enthalpies of formation. We have also calculated their projected operating potentials, or the potentials that can be used when they are in operation. Then we can see that the PBCM structure as well as the IMA structure, they've got a very large volume, which also offers good volumetric capacity. And then also, it can also offer favorable diffusion channels and also superior rate capacity as compared to the FD3M, which is a cubic structure. The other 2 are orthorhombic structures. And then when we look at the enthalpies of formation, just to investigate how stable they can be, we see that still the PBCM structure offers good stability, since their enthalpies of formation is negative. And then also the other ones as well, they have got good thermodynamic stability, but not as good as compared to the PBCM. And then we calculated the projected intercalation potentials. We find that they fall within the prescribed pulse discharge range of 2.7 volts and also 3.9 volts. And then also we have noted that they are very much comparable to the ones of lithium-ion chemistries, which normally range from 2.97 to 3.5 volts. Then what does this tell us? It tells us that now these structures are able to reversibly insert and also remove calcium without any distortion on the material. So we have also went on to calculate their stability to see how the atoms vibrate when the material is also in operation. We have seen that the PBCM and also the IMMA compounds, they offer good dynamical stability as well as mechanical stability, which means that in terms of safety, now these structures are very, very much preferable. Then the FD3M, it does have some negative vibrations along the high symmetry directions, but they are not as severe as one would think. So then probably all of them, they show good promise when it comes to mechanical and also dynamical stability. So we went on to determine the electronic conductivity. This one is being determined by measuring the size of the band gap. We know that materials with band gap are insulators. The materials without the band gaps are either semiconductors or conductors. So when we look at the FD3M, we see that no, it has a band gap, so it may not be a good conductor. And then we look at the PBCM and also the IMMA. We see that they do not have a band gap along the Fermi level. That means that now the electrons are allowed to jump from the valence band to the conduction band, which attributes to good conductivity. So then that's what we have seen with these materials. So then all these properties that we have calculated so far, they are pointing towards the PBCM and also the IMMA as the preferable or the suitable structures for cathode materials. So for the cathode materials, we can summarize by saying that we have identified these two polymorphs in particular to be preferable or suitable for application as host structures for calcium ion batteries. And then we also have some future work that we are still going to do, because this is just a master's work, but we would like to extrapolate it and do other calculations. So we still have to do the stress strain effect. We still have to do the open circuit voltage. And then we still have to do the diffusion barriers and also the channel sizes, of which up to this far we have no idea how we're going to do it, but we believe that we'll find a way of doing it. And then we'll also like to do the cycling performances. So then that's, in a nutshell, all about the cathode materials. Now we come to magnetic materials. The magnetic materials that we are looking at the bimetallic magnetic materials, which is a combination of manganese and platinum, iron and platinum, cobalt and platinum, chromium and platinum, and also nickel and platinum. So then these materials are promising materials for application in magnetic systems. So then they exhibit very, very good properties when it comes to their application in magnetic systems. So we have learned from literature that these materials, they've got high magnetocrystalline anisotropy, and also in the work that we have done as well. So then this makes them to be ideal for advanced magnetic storage devices, such as the hard disk drives, the sensors, and also in spintronic devices. So they also have high cohesivity. They also have good thermal and also mechanical stabilities. So these are the other properties that makes this material to be good. So I think I will skip through that one. So these are just the applications, so then they can be applied in both optical devices and also in biomedical devices. But our interest is mainly on this one of magnetic data storage. We're not going to focus on the biomedical applications. So we have done some results, some calculations on these structures or these alloys. Then the first work that we have done was on the FEPT alloys. So we have done various compositions according to how they occur in nature. And then we have seen that with the calculations that we have done, if you can look at the percentage difference of the experimental volume as well as the calculated volume, you see that there's no much difference. It means that our calculations were able to reproduce what has been found experimentally. So we went on to test their thermodynamic stabilities by calculating the enthalpies of formation. We find that enthalpies of formation are negative, which shows good stability. Then we went on to calculate the magnetic moments just to determine how magnetic they are. We see that they've got various magnetic moments, and the magnetic moment of the equiatomic composition, which is FEPT, we find that it was very much in good agreement with what has been found experimentally. So then it means that now our approach was able to reproduce what has been found experimentally. And then we find that now this equiatomic one also have got the least magnetic moment. So then this is going to lead to durable magnetic hardness, as lower magnetic moment implies higher hardness parameter. So this can make it very much suitable and also efficient for permanent magnets. We also went on to calculate what we call the magnetocrystalline anisotropy, which is the energy difference between two axis directions of magnetization. So then what we basically do is that we tell our system or our CASTEP or the code that we are using to simulate that we want you to optimize the structure along the 001 direction, optimize the structure along the 100 direction, and also the 1 direction. We have also done other directions, but we could not find any significant difference. Then when we calculate, when we optimize the structures along those directions, we were determining the energies. So then the direction with the least energy, we call it the easy axis direction, or that's the direction where it is mostly magnetized. And what we go and do is that we subtract the least energy from the other energies. So then in subtracting the least energies from the other energies, these are the values we find. So then these ones that are dashed, it means that this one is the least energy, and then the other ones were higher. Then we see that for the equiatomic structure, the magnetocrystalline anisotropy were very much in good agreement with what has been found structurally, experimentally. And these are the ones, this is the structure that has got the highest MCA, or magnetocrystalline anisotropy, which makes it very much essential for the design of magnetic recording devices. So we have also done other composition, manganese, cobalt, and also nickel. This study is not as advanced as compared to the one of iron and also platinum, but we have seen that they also give us good magnetic moments, especially the manganese platinum is very much comparable to the one of iron platinum. And then also, they also give us negative enthalpies of formation, which shows that everything is stable. So we have also went on to calculate the electronic structure just to determine the confirmation of what we have found magnetically. So normally the electronic structure tells us how magnetic moments are going to be. So let's just look at the last one, which is the nickel platinum. It has got the least magnetic moment. Then you can see that the spin up states and also the spin down states, they are almost symmetrical, almost the same. So that means that their magnetic spins are almost canceling each other. Hence, it has the lowest magnetic moment. So that's what we have seen. So then this is what we can conclude about the magnetic alloys. So we have found FEPT and also MN to show excellent magnetic properties. This is the work that we have done for Itemba Labs. So this is the experimental work, and then this one is our computational work. They just wanted us to see for them if there is any diffusion on V2O5 of oxygen, and then we have seen that indeed at 0 GPa you have got V3O5, and then when you go further, and then you see that you have got more bonds as compared to what you have initially. So then we concluded for them that yes, it's true, oxygen does some diffusion as you increase the pressure. Achievements so far, what we have done as a group, since 2022, we have managed to have 5 publications in peer-reviewed journals, and then we also have one of the work that I've just presented here on cathode materials, which is under review. We also have 1 conference proceeding, and then we also have other 2 that are accepted. We have presented our work in 6 conferences, and then we also have 1 master's completion, and then 1 Bachelor of Science honors as well. 5 Bachelor of Science honors completion. So then these are some of the, these are the papers that we have published utilizing the resources of the CHPC. The challenges, well, our challenges are common. The first one is the long queuing time when we submit our jobs. And then the second one is the one of student funding. We're really lucky when it comes to the funding of postgraduate students. Though we have funds for the projects themselves, but for the students it's very difficult. And then we also experience poor network during peak time in such a way that when the jobs complete, it's difficult to download them. But however, with the assistance of Anton, we have been able to retrieve those jobs. And then for the near future, we are looking to have at least 1 postdoctoral fellow. And then we are also looking to expand as well and have collaborations, possibly somewhere here, with other institutions so that we can widen our scope of research. I'd like to appreciate Nikis for the computational resources, the University of Fort Governbeki Research and Development Center for funding, and also the NRF as well for funding, ESCOM as well for their funding. Thank you very much.